Space lasers. I know, it sounds like something straight out of a sci-fi movie, right? But what if I told you that this isn't science fiction anymore? What if the next big leap for the internet, the very connection you're using to watch this video, is powered by lasers beamed down from space? Forget everything you know about fiber optics and 5G for a moment. We're talking about a technology that could connect every single person on Earth, no matter how remote, with speeds that would make your current connection look like a dial-up modem. This is the story of Space Laser Internet, and it's going to change the world. To understand why space lasers are such a game changer, we first need to look at how our internet works right now. Most of the global internet is carried by a massive network of undersea fiber optic cables. These cables are incredible feats of engineering, stretching for thousands of miles across the ocean floor, transmitting data as pulses of light. On land, we have more fiber, along with cellular towers that use radio waves for services like 4G and 5G. It's a complex, expensive, and fragile system. Laying a single cable across the Atlantic can cost hundreds of millions of dollars and takes years. Plus, what about the places these cables can't reach? Think about remote villages in the Himalayas, small islands in the Pacific, or research stations in Antarctica. For them, reliable, high-speed internet is still a distant dream. This is where satellites come in. For decades, we've used satellites for communication, but they've traditionally been slow and expensive. You might remember the old satellite internet services with massive latency, making video calls or online gaming a nightmare. That's because those satellites were in geostationary orbit over 35,000 kilometers away. The signal had to travel so far that there was a noticeable delay. But now, we're in the era of low Earth orbit, or LEO, satellite constellations. Companies are launching thousands of smaller satellites that orbit much closer to Earth, just a few hundred kilometers up. This drastically reduces the latency. But even these new constellations primarily use radio waves to communicate with the ground and with each other. Radio waves are reliable, but they have their limits. They spread out, lose strength over distance, and the available radio spectrum is getting crowded and heavily regulated. Enter the space laser. Officially known as free space optical communication, this technology replaces radio waves with highly focused beams of light lasers to transmit data between satellites. Imagine a network of satellites blanketing the globe, all interconnected not by radio links, but by a web of invisible laser beams, creating a true mesh network in space. So, how does it actually work? Each satellite is equipped with a sophisticated optical terminal. This device has to be incredibly precise. It has to locate another satellite hundreds or even thousands of kilometers away, lock onto its target, and then transmit a laser beam with pinpoint accuracy. This is like trying to hit a coin from over 100 miles away, while both you and the coin are moving at 17,000 miles per hour. It's a staggering engineering challenge. These terminals use advanced gimbals, mirrors, and tracking systems to maintain the connection, constantly adjusting for the satellite's movements. Why go to all this trouble? The advantages are immense. First, speed and bandwidth. Light travels faster in the vacuum of space than it does through glass fiber optic cables. While the speed of light in a vacuum is a universal constant, it slows down by about 30 to 40% when it passes through the glass of a fiber optic cable. This means a data packet sent via laser link from London to Tokyo through space could theoretically arrive significantly faster than one sent through undersea cables. Furthermore, lasers operate at a much higher frequency than radio waves, allowing them to carry vastly more data. We're talking about terabits per second from a single link, an almost unimaginable amount of bandwidth. The second major advantage is security. Radio waves spread out, meaning they can be intercepted. A laser beam, on the other hand, is extremely narrow and directional. To intercept it, you'd have to physically place something directly in its path, which is practically impossible in space without being detected. This makes laser communication inherently more secure, a feature that's incredibly attractive for military, financial, and governmental applications. And finally, there's the issue of regulation. The radio spectrum is a finite resource, and getting licenses to use it can be a complex and expensive process fought over by governments and corporations. The spectrum for light is, for all intents and purposes, unlimited and unregulated. This allows companies to deploy their networks faster and with more freedom. The global impact of this technology cannot be overstated. We're talking about bringing high-speed, low-latency internet to the nearly 3 billion people who are still offline. A farmer in rural Africa could get real-time weather data and market prices. A doctor in a remote Amazonian village could conduct a live video consultation with a specialist in a major city. Children in a school on a tiny Pacific island could access the same online educational resources as a child in New York or London. This isn't just about faster streaming for Netflix. It's about leveling the playing field for education, healthcare, and economic opportunity on a global scale. It creates a world where your geographic location no longer determines your access to information and opportunity. Of course, this futuristic vision isn't without its challenges. The primary obstacle is atmospheric interference. Laser beams can be distorted or blocked by clouds, fog, rain, and even atmospheric turbulence. You can't just point a laser from a satellite directly to a laptop. To solve this, the system will likely be a hybrid. The laser links will form the superfast backbone in space, but the final connection down to the user on the ground will still use more resilient radio waves. The satellites will beam data down to local ground stations, which then distribute the connection to users in the area via traditional means. Another challenge is the sheer complexity and cost of the hardware. The optical terminals on each satellite are incredibly sophisticated pieces of equipment that need to function flawlessly in the harsh environment of space for years. The pointing, acquisition, and tracking technology has to be perfect. A tiny misalignment could cause the link to drop. Scientists and engineers are working tirelessly, developing adaptive optics and advanced algorithms to correct for these disturbances in real time. There's also the problem of space debris. A collision with even a small piece of debris could destroy a satellite and its precious optical payload, creating a cascading problem for the entire network. So, who is building this future? Several key players are in this new space race. SpaceX's Starlink is perhaps the most well-known. They have already deployed thousands of satellites and have begun equipping them with laser links, creating one of the first operational mesh networks in space. They've already demonstrated their system's capability by providing internet to researchers in Antarctica, one of the most remote places on Earth. Amazon's Project Kuiper is another major contender, planning its own constellation of over 3,000 satellites with a similar laser-linked architecture. And it's not just private companies. Government agencies like NASA and the European Space Agency are also heavily investing in laser communications, not just for Earth orbit, but for deep space missions. Imagine streaming 4K video live from Mars. With laser communications, that becomes a real possibility, enabling a new era of space exploration. Looking ahead, the vision for space laser internet is truly awe-inspiring. We can envision a future where instant, ubiquitous connectivity is as common as the air we breathe. Smart cities will run on a seamless flow of data from billions of devices, optimizing traffic, energy consumption, and public services. Autonomous vehicles will communicate with each other and the network in real time, making transportation safer and more efficient. The Internet of Things will finally reach its full potential, not just in our homes but across entire industries, from agriculture to manufacturing. And the network won't be confined to Earth. As humanity expands its presence to the Moon and Mars, these laser networks will extend with us, creating an interplanetary internet. A research base on the Moon can have a direct, high-speed link back to Earth, allowing for real-time collaboration and control of robotic systems. We are standing at the dawn of a new communication age. The transition from radio waves to light in space is as fundamental as the shift from copper wires to fiber optics was on the ground. It's a monumental undertaking, filled with incredible challenges, but the potential rewards are revolutionary. It promises to connect the unconnected, accelerate innovation, and bring humanity closer together in ways we're only just beginning to imagine. The internet powered by space lasers isn't a distant dream. The satellites are being launched, the lasers are being fired, and the future is being built, one beam of light at a time, right above our heads. Thank you so much for joining me on this journey into the future of the internet. If you're as excited about this technology as I am and want to stay updated on the latest breakthroughs in science and tech, make sure to hit that subscribe button and turn on notifications. We've got so much more to explore together. See you in the next video.